So, Roam Our Users is part of a worldwide network that is sponsored by the R Consortium and the Linux Foundation. And our group has already held a number of in-person events in Rome, but we felt it was time to venture out into the online world. But now I would like to introduce our guest speaker, Jakub Nowosad. He is an associate professor at the Adam Mickiewicz University and a visiting scientist at the University of Munster. Jakub is a computational geographer working at the intersection between geocomputation and the environmental sciences. His research is focused on developing and applying spatial methods to broaden our understanding of processes and patterns in the environment. He is an active member of our spatial community and a co-author of the books Computation with Python and, best of all, Computation with R. Luckily for us, he also enjoys teaching and is here tonight to talk to us about using R for geospatial predictive mapping. Jakub, we are absolutely delighted to have you here at our first online event for Roam Our Users group. Everybody, if you have any questions, please feel free to write them in the chat, and then we will perhaps try to get round to those at the end. So, Jakub, over to you.
Thank you a lot, Lucy. Hello, everyone. I'm here today to talk to you about the topic of spatial data in R, and especially about the topic of predictive mapping. And predictive mapping is a very specific term that I will maybe explain later. But for now, let's just focus on R and spatial data that we can work with in R. And similarly to data science, we often think about spatial data science and about connection between R and different domains that use spatial data. Because spatial data is to some degree unique, but also is very general. You can find spatial data in different shapes and forms in different domains. And any one of you today on that meeting, you can think about your domain and how spatial data can be defined or found in the problems that you have. And this spans from problems from environmental sciences that are closer to my regular work, but also goes to social sciences, to journalism, to ecology, transport, and many, many others. And then we, of course, have methods. So we try to think about how to solve specific problems. And we can think about those methods in a very general sense. So we can think about those methods in a sense of exploratory data analysis. So we want to explore our data, but with this spatial view. So we want to look at, for example, if our coordinates are correct, if our data that should be, for example, in Germany is not by accident showing up in South America or the other way around. Then we try to process our data, maybe clean that data a little bit, maybe add some variables, maybe connect some information together. Then we have some specific data transformations that are related to spatial data. It includes, for example, changing projections. So we could find data with different projections and want to unify them or move them into a projection of our choice. Very special part of those computational methods is about visualization. So in short, making maps. And it's November, there's this 30 days map challenge. People are making tons of maps. And this is a core part of the work because maps, of course, are a tool that can be used at any stage. So we just have a new data, we map this data, we look at the visuals, how this data look, if this data is correct or not. And then we do that internally inside of our workflow. And then at the end, the map could be also the outcome of some of our projects. With spatial data, we can also think about developing web applications. For example, in R, it's with Shiny. And in general, it's about software development. So we try to develop some R packages to share new methods, to share new ideas, to be able to collaborate on tools. But today, I want to focus mostly about its general term of spatial data analysis and modeling. And this term can be defined in many, many different ways. And there are many sub-topics that we can define here. But today I want to focus mostly on the problems related to spatial modeling or spatial interpolation. And I will show you that in a few minutes. But before that, before we go into the details of a specific problem, let's maybe just look at the resources that maybe you can use if you are interested in those topics. This is a thing, we're in the situation, I think it's in a very nice situation that was not here 10 years ago, that there are many resources that you can look and you can read. And all of those I'm showing you now are free, available online. And that shows you either general ideas behind the spatial data and methods, or very specific ones. So here you can see some of the books that are publicly available about urban accessibility, or analyzing census data, or looking for at the satellite images, or analyzing the data, spatial data in general. There are also many online courses that are available online that you can go and look at their code, you look at their examples. There are some YouTube channels. There is a OpenGeo Hub Foundation, which is recording the many talks and workshops that they are organizing, that you can also learn a lot. And on social media, there is a hashtag called rSpatial that also allows you to share your spatial R outputs, but also discuss some problems or questions that you may have. And talking about those resources, I just want to highlight you a project called GeoCompX. So GeoCompX is a project that started in 2016 with me and Robin Lovelace. Started working on this book called Geospatial with R that we co-wrote with Janusz Müncher. And this is a book that was recently published as a second edition this year, but also has several translations, some of them made by the community. But most importantly, the book is freely available online at r.geocompx.org. And then I think this book can get you started to work with your data, with your spatial data and try to help you to understand this data, help you to understand what you can do with this data, and what are the pitfalls maybe you can find. But this project started just as a book project almost 10 years ago, but nowadays it's a slightly larger community effort. We have books not only about R, but we have a book about Python as well, and there is a work on geospatial with Julia. And this part of the project is about books, but our GeoCompX project is also about other resources. So we have blog posts. So those blog posts, the main general idea is that those blog posts are about geocomputation with a programming language. So it's a very broad category. We have a GitHub organization where you can find our resources and their source code. And then we also have a Discord channel that is a place for discussions or asking questions or sharing your projects. And so what I wanted to do before showing you a use case is that I wanted to show you how you can contribute to that. So this is a community-driven project, and I would really encourage you that if you have any ideas that you think that could be improved or implemented or added into this project, you can just get in touch with me or open an issue on GitHub or contact me through social media. But it's also about fixing things that are already there. So I'm sure that there are some typos or maybe some things that are not clearly enough explained that we could improve. As I mentioned before, there are some community translation projects that translate those materials to other languages. I think it's very valuable, and it would be always great to expand that. And finally, especially with blog posts, we also accept guest blog posts that then we try to read and try to maybe give some inputs to those, and then we publish them on the geocompx.org website, and other people can read, other people can learn, and other people can share your knowledge. So I would encourage you to take a look at the geocompx.org. And if you want to learn more about these projects, there are some previous talks I gave last year. And there is one of the talks was also recorded, so I would encourage you to look at that. But let's move to the core topic for today. So the core topic for today that I wanted to talk about is about predictive mapping with R. So what was the idea here? So I will be talking about this kind of a problem that we have some measurements. So we have some measurements in space. And for our measurements, we have some information. We have some values that we gathered, collected, or someone else collected. But we don't know what's between them. We don't know what's the value, what's the actual number in the place between our measurements. So here we want to create a continuous map from our point observations. In other words, we want to label every pixel. So we want to label every place. In this case, you can see on the right in South America. And our problem actually is about predicting species richness. So we have some plants, and for a given area, we count how many different plant species we have, and this number is basically a species richness. And you can see we have many measurements in South America, and our idea is to get this continuous map for the whole area. As you can see on my slides, maybe I should mention that before, you can find all of my slides at my website /Rome 2025. But most importantly, on many slides, you will have this code text, which is basically a folded code that you can use to reproduce all of my slides. So all of the slides have this code that you can take a look and reproduce. So here we'll be using this data that you can see here is an example data from the cast package in R. And you can see that we have different values in different locations from 0 to 300, more or less. And for the purpose of this talk, I will divide this data into two groups. So 70% of the data will be moved as a training sample, and the remaining 30% will be randomly split, and it will be used as a sample. Sorry, I have some technical issue. I hope now it's better. So yeah, this is our situation. We have our training data, we have our test data. And here we will have our predictors. So we have our point data. This point data is available only in some locations, but then we also have this predictor. So we have data about the whole area of South America. And this is 4 different data sets. So the first data set is about temperatures, about the differences between high and low temperatures. And then we have 2 set of information about precipitation, about annual precipitation, about precipitation of the driest month. And the 4th one is about the elevation. So for each location, we will have information about elevation. And all of those data sets are from the geodata, our package that allows you to download data about those climatic variables and elevation. And in our case, we want to predict that for the South America. So this blue area here is our area of interest that we want to predict. And then we have this table that you can see on the right. And this table is what we will be using for our predictions. So here, what we'll be using for our predictions is just a very simple table with our species richness, so the value that we want to predict. We have some of the predictors that you've seen on the previous slide, and we have coordinates. So for each point, we know what's the location of that point. And then there are many methods that were developed for that task. So we have this task, we will have our points, we want to predict them, and there are many methods. And let's look at 4 of those methods. So the first method I want to show you is called IDW. So it's an inverse distance weighting method. And this is a very simple method that only uses our information from our points and one parameter called IDP. And this parameter, this power parameter, basically represents influence of each point. So if this parameter has a low value, it basically means that we give a lot of influence over a large area for each point, meaning we also smooth this map. But if this value is high, we basically give this influence only in a smaller area, and then our points only influence those areas around them. And you can see on the right, this is the outcome of this approach. So what we do here, we just specify our variable in this model, and we specify what this parameter value is, and then we predict our value in space. And by default, it will predict to this rectangular area. So I map this only to South America, and finally, I visualize that with an R package called tmap. And here you can see this is our prediction using this method. Then another possible approach, slightly more complex, is related to various geostatistical methods. And one of the most basic of those methods is called ordinary Kriging. So this method is similar to the previous one because it only uses the values of the points. There is no external information used. But this approach is based on this visual that you can see here. So this visual is called semi-variogram, and it represents a relationship between the distance. So this is the distance between our points and a semi-variance. So in this case, how dissimilar the values are in our points. So what we need to do here, so first of all, we create this kind of visualization. We're using, for example, our package called gstat, and then we model that. So this blue line is a modeled line. So this line basically tells us that if our points are very close to each other, they are fairly similar. But then if we go farther and farther away, and we look at farther points to us, then the values are less and less similar. And this is an information that we can give to the model. And here I'm just using this kind of automatic approach with a function called fit.variogram that fits this model. And then finally, we can do predictions. So with these predictions, we provide this model that we created. And again, we just put this model on our map. And you can see this is the outcome that we developed. So this is this map of the ordinary Kriging. And then
Sorry, we cannot hear you anymore.
I still can't hear. It just suddenly cut out.
I cannot hear his voice.
Mm.
I can see the video and the slides, but I cannot hear the voice.
Yeah, we can see everything, but we can't hear you.
how about now?
Ah, yes. Perfect. Okay.
Yes,
carry
now
on.
it works. Thanks.
Yeah, I think there is some issue with the external camera, but hopefully it's gone now. So let's move to the second method. So this method is called universal Kriging. And with this method, we try to also include the values of other variables. So now we are not only interested in the values from that we previously used, so only of the point values, but now we also use the values of our temperature and precipitation and elevation. And then the steps are exactly the same. We create the semi-variogram, we model the semi-variogram, but you can see it looks slightly different than the previous one. And finally, we use this new model that take care not only of the values and the relationship between the values in space, but also takes care of the relationship between the values of our species richness and our predictors. And here is the map that we can create with this approach. So those were like three approaches that are very much based in spatial data analysis, because all of those three approaches, they know that our data is spatial. They know that there are some relationship between them. They know that some points are closer, some points are more apart. But often what we do, we often use machine learning. So with machine learning, or at least those traditional machine learning approaches like random forest, but also with statistical learning, like just try to think about linear models. When we use those kind of methods, then those methods are based on a table. They don't know that our point 1 and 2 are next to each other or on the other side of the continent. It just tries to learn the relationships, sometimes very complex relationships between our outcome and our predictors. So this is a totally different approach, but we can also do that. So what we do here, we just train, in this case, I just train a regular random forest model for the species richness variable based on those 4 predictors. And I predict this information in space and created this map. So you can see we have those 4 different approaches. And now I think we go and we can think about this important question. And this question is, so which one is the best? So we have 4 maps. We created 4 different results. We used 4 slightly different approaches from IDW, which is only based on our points, to ordinary Kriging, which is also based on our points, but also on our model. Then it's universal Kriging, which is based on the model, but also relationship between predictors, external predictors. And then it's random forest, which has no idea about the spatial relationships, but can learn those complex relationships inside of the data. So, so please take a look at the map. So and then maybe you can just quickly write in a chat, what do you think is the best map just based on this visual? So what in your opinion would be the best map here? And then, so this is just based on our map. But now let's maybe add some numbers. So you've seen that at the first step, I divided the training data and testing data. So I put this 30% of the testing data aside. So then what I can do, I can just look at this testing data and compare my testing data with my predictions. And I can put some numbers. So here what I've done, I calculated RMSE. So this is a measure which basically says what's the error in my prediction. And the best one is close to 0, and the larger value is less good. And you can see here, those are the RMSE values for my 4 methods. And you can see here that each of those 4 methods have different RMSE values, with universal Kriging and random forest having fairly similar, but based on the RMSE, the lowest value, so the most preferable value, is of the ordinary Kriging. But if we look at the maps, I don't know about you, but for me, the map with universal Kriging or the map with random forest look better, look more detailed, while the ordinary Kriging is very smooth. So then the question is, which of this map is the best, which one we should select. However, if we actually take a longer look and we think about this problem for a little bit longer, there are a few issues that we have in estimating or deciding on that problem. And I will show you 3 main issues that we have currently. So the first issue is with the predictions of mostly of the universal Kriging. So take a look at the legend. You can see that our legend basically goes from orange for the values below 0, and then it's different shades of green and blue for the values above that. And what we can say basically is that we can basically say that in universal Kriging, we have a lot of those orange areas. And those orange areas are the negative species richness. What does it mean? Doesn't make any sense. Like, species richness represents how many plant species we have in a given area. It's impossible to have a negative value. So this suggests that definitely something is wrong there. Then there is second issue with our training data. Because look at our training data. Our training data is not located in every location in the same way.
we have huge areas in South America that we do not sample, but we want to predict there. And this is an issue because we have the points close together, but we want to predict from those points, we want to predict far away. And this is underlined on this figure on the right, where you can see two distances. So the green distance is a distance called sample to sample. So basically, it's a density of the distances between our training points. And this orange one is a distance between our points and the places that we want to predict. And you can see that we want to predict far away, even though our points are usually close to each other. And you can do this kind of plots with the cast package. There is a function called geodist that allows you to calculate those kind of diagnostics. And this is about distances in actual space, in so-called geographic distances. But we can also think about future space. So think about the values. And if we look at those, we can see that the points, so look at this blue density. This blue density tells us that our points are usually fairly similar to each other. So they have similar temperature, they have similar precipitation, etc. But if we compare our points to the places that we want to predict, so this red distances, they are much larger, meaning that our points and the places we want to predict are often not very similar. And this is a problem. And the third related problem is about our testing data. And this problem is that our testing data is spatially clustered. So we have some locations with our spatial data that we have a lot of points, like here, for example, in the north part, but they are vast areas without any sample points. And because of that, we are not evaluating this map properly because we evaluate only just parts of the actual space we want to understand or we want to predict. And it's highlighted here on this figure on the right, where our test sample, so this pink density, is exactly or almost exactly the same as our training density, which basically says that we validate our model in the same locations, the same spatial relationships as our training data, but our prediction space is much, much farther away. So we are not validating in this prediction space. So now we have three issues. Gladly, the first issue is only visible in one of the methods. So maybe we can just say, okay, maybe don't use universal Kriging, or in those areas that it's negative, just say, I don't know what's there. But we can work on the issue number 2 and number 3. And I will show you how we can think about some solutions to those problems. So how can we actually, because our main problem is how we can actually reliably evaluate our models. So how can we address those issues, and how can we say which model is actually the best, and also what's the actual quality of each of those models. And there are several approaches that we could have. Like the most obvious approach is that, okay, let's just have better training and testing sample. Because if we just have a random training sample, so we have points all over South America for both training and testing, then we represent the whole area, then our estimations are better, and then our robustness of the model is also better. However, of course, especially in like environmental sciences, but also many other fields, it's impossible. We don't have many points in the middle of Amazon, for example, or on top of the mountains in Andes. So this is a great solution, sadly not often possible. So are we lost? Is that this is down the end? Gladly not. So there has been a lot of work in the recent years of how we can think about this problem and how we can improve it. One of these ideas is called area of applicability, and this idea and the whole problem that this idea tries to solve is to think about this issue about that we have some areas that we can predict our model to because those areas are similar to our training data. So we have training data. For this training data, we have temperature, precipitation, and so on. So we know that if precipitation is 500 millimeters on elevation of 100 meters, etc., we know those relationships. So for those areas, we can make predictions. But also then we can say, but if in my training data, I've never had a precipitation of 3000 millimeters, but there are some areas in South America of that precipitation, maybe don't predict there. And that's basically the idea of area of applicability. So this idea can be just taught in this way that we have our training data here in those white points, and for each training point we have information about precipitation and temperature and elevation, and then we look for every other area in our prediction space, and we say, is it similar or not similar to our training data? And here you can see that everything in this dark threshold, and then we can say, okay, so some areas are similar to our training data, so we can think, okay, I can predict there, I can be fairly certain that my prediction is well there. And then we can also say some areas are totally different from the areas my training data have seen. So for this area, we probably should not make predictions. And you can see that here on the right, where those areas that we think that we know those relationships are in green, and those areas that are very different from our values in training data are in 0. So those areas, we basically say they are too different from what my model have seen. So probably I should not guess there, because that's a guess. We don't know what the actual relationships that are in those locations. So probably we should think about our predictions in this sense. We shouldn't think about our predictions using those full maps that you've seen a few slides ago, but we should think about them in this way, that we should mask areas that our models have no idea about, that are basically, those are areas with a different environment from the environment that we measured. And you can see this gives us a much different look. And maybe it's not as satisfying. We are not providing a full map, but we are more trustworthy because actually our model only know about those areas and not those gray areas. And then there is another issue about testing points. So as we already mentioned, our testing data is clustered, so we cannot actually be sure about our RMSE estimations, because our RMSE estimations, they were based on those cluster samples. So they put more emphasis on the points close to our training data, but has no idea about what's the actual quality of our model in the middle of Amazon. So what we want to know, how exactly is reliable our model is exactly in the locations that we can predict this model for. And how can we do that? And there are several approaches that are being proposed. And those newly proposed approaches includes the approach called KNDM. So it stands for K nearest neighbor distance matching. But in general, this is an idea that we try to adapt our validation method to our prediction. So in our case, we want to have validation for our whole area that we want to make a prediction. And you can see here on this figure here that our distances from our points are very close to each other. With this orange area, those are the distances between our points and our prediction space. And then this blue density is cross-validation density using this method. So this density, you can see it much more similar to the orange one, so the one we actually want to apply. But I know this may be hard to understand. So how exactly this method works? So what's the idea behind this KNDM method? So the idea behind this method is that depending on how our sample looks, this method adapts to it. So take a look on the panel on the left. So if we have a random sample, what we can do, we can just split our points into basically a simple random key-fold validation. So we will have, for example, 4 groups of points that we will create our model, and then we'll test this model on the 5th fold, and then we'll move this held out fold, and then we will build a model of the folds from 2 to 5 and predict on the 1st, and we'll repeat that process 5 times. And this works when we have a random sample. But in case of other samples, like in our case, we have a sample probably like this. So it's a cluster sample, meaning that there are many points close to each other, but there are also many areas without any points. Then what we want to do, we want to predict on the group of points that are far from each other, because this is the actual prediction situation we want to apply. We want to predict our model far away. So we should also validate that model in that way, that how our model will behave if we only build the model on the, for example, folds here and want to predict them on the folds here. And again, we do that many times and average the results at the end. And this way is a much more reliable way, because then our model is not learning, okay, so I have a training point here and testing point here. So then it's basically just reading almost the same value. And then the model quality is too optimistic. But with this approach, we actually adjust the situation. So we adjust to either random or spatial cross-validation. And with this approach, we actually get the statistics that are more reliable. So let's do that. We can apply this approach with using the function from the cast package. So the cast package has this function called KNDM, which you can find here. And you basically provide your spatial data, your predictors, and say how many folds you want to have. And then it will just look at how your points are distributed, and then will adjust to that. So it will provide you this proper division of those points. So then let's look at the final map. So now we can finally look at our map. And for this example, I just decided that we'll just stick to the random forest, but we can also use this approach for the other methods. And you can see we have our map on the left, and we have our RMSE of 27.42. And this is how often you can find different reports or scientific publications doing that. They will provide you with some measure like this RMSE, and they will provide you hopefully with some map, and you will see this map. But what I want to highlight here, that maybe it's not the best approach. Maybe we should not do that. And hopefully you already know why. Because there are two issues. Our model has no idea what happens here in the high mountains, or what happens here in parts of Amazon. Our model never seen this kind of relationships in the data. This environment was not studied. Our model has no idea. And also, we estimated this RMSE based on our cluster data. So we could get training and testing points next to each other, which will put this number to be too optimistic, overly optimistic. So what should we do? We probably should do this way. So we should not give the values for every location in our area, but we should only provide the values for the locations that our model actually learn anything, because actually we can only say something for those areas because we don't know what are the relationships there. Of course, you can look at this map on the left now and say, okay, maybe this could be an indicator of where we should do our new measurements, where we need to go and check and add something, where our understanding is limited. But probably we should not provide the value there because we don't know what actually happens there. And secondly, as you can see on the right, the proper value, the RMSE, based on this prediction domain adaptive approach, is larger. So it's not 27, it's closer to 35. And this is actually much more appropriate, much more close to the true value. Because we don't know what are the actual values for the whole South America. But this is the estimation which is closer to the truth. And I think we should aim for that. We should aim for the proper, robust estimations and validations. And you can see we can do that, but it's not always that straightforward. And it's not always that we'll be able to predict for the whole area, and not always this value of RMSE will be the nicest we see. But we should not lie to ourselves, and we should try to do that in the best approach possible. So let's maybe take a step back and think about this problem in general. And think about different scenarios. So what are the scenarios we could find in real life, and how we should adjust to those scenarios? So the most optimistic scenario that happens in some fields or some domains, and in some domains they are almost impossible, is that you have an independent testing set all over the prediction area. Meaning that you train your data, you train your model on some data that you collected or someone else collected. You have your model never seen this testing set, and this testing set you got from an external source. You never had any connection with that, and then you test on this independent testing set. And this testing set is spread all over your prediction area. This is an ideal situation, because with this ideal situation, your estimation of the model quality will be the best. Then you can actually say if your model is good or bad. But as I said, this is a rare situation. So let's look at the second situation. We have a lot of samples. Our sample is random or in other ways, probability sample. And then we have a lot of points, and our points cover the whole area. So if we have this situation, what we can do, we can just, or what should we do? We can just split our data. So we should put testing points aside. Maybe we should have 2 or 3 groups, so we could have a testing and training, or we could have testing and validation and training. But if we have this kind of situation, we just put some part of data aside. We never use the data for training. We never use the data for anything else but only for the final model evaluation. And then it's a very nice situation. Then also we can get reliable statistics. We can also get a reliable estimation of our model quality. Next, we are now going into more common situations. So now, next, it's a situation that you've seen me talking about for the last hour, and this is a situation that we have cluster sample. So we have cluster sample, and then we do the split. But in my slides, what I've done, I just done this very simple approach. I just split my data randomly into training and testing. But there are better ways. We should split our data to resemble our prediction situation. So in our case, if in our prediction situation is that we want to predict for areas far away, random split is not good. Random split is great when you have random sample, but if you have a cluster sample, random split will be overly optimistic. And the other way around, if we have a random sample and we do this approach, it will be overly pessimistic. So what we should do, we should adjust our split based on the problem, based on the prediction scenario we have. So in this case, we can just use this KNNDM method, and this will split our data into training set and testing set, which you can see is often far away from each other. Meaning that then if we build our model on those blue points, and then we test it on the red points, we will get a proper evaluation of that. And of course, this evaluation should be only for the areas that are supported with this approach of area of applicability. Next, it's a slightly worse scenario, but also happens. What should we do when we have a small sample? So we have small sample, so create a proper model and part of it into a testing set. Because if we do that, we have just a bunch of points and our model is very, very weak. And those are practical situations. So what can we do here? We can do should be based on our prediction situation. So in this case, you can see this is a prediction situation when our faults are far from each other, because we also want to predict to places far from the points we have. And this is worse than the previous approach, because we use the same points to build the model and to evaluate it. So then our evaluation could be good as in the previous approach. But again, we have a smaller sample. And finally, if we have even smaller sample, but we don't know what kind of parameter should our model use, or maybe we want to do a model tuning, so we want to maybe select also do a feature selection, etc. Then we can also do this approach. It's definitely not the best way in general that we can do, but often it's the only approach we can have. So try to think about it given your situation. If you are in that first situation, that's the most optimal, and then you have some solutions, and then you can look at the next scenarios and try to think to which scenario your problem is closest to, and try to adjust to that. So just to maybe close on the R topic. So you've seen some of the R code that I quickly shown, but I didn't want to explain every line of code. You can look at the slides and you can try this code by yourself. But with this, with R, there are several tools and several groups of packages that can help you with that. In the Chrome task view called Analysis of Spatial Data, there is a section about that, about spatial machine learning. And it gives you some examples, including 3 main machine learning workflows in R, including packages like Caret, MLR3, and Tidy models. And for each of those, you have also spatial tools like cast and block CV packages, like MLR3 spatial temp CV or spatial sample, that allows you to do this proper cross-validation or apply this area of applicability approach. There are also tools that I do not have time to explain in details, but there are also methods that try to take concepts from machine learning, but then also put those interactions between our locations there. So there are packages like Spatial RF, like Random Forest GLS, like Meteo, like GPBoost, which try to do that, which try to connect machine learning and spatial awareness. There is also a blog post series me and my colleague wrote earlier this year about machine learning for spatial data with R. This is a 6-part blog post series showing those different tools and how you can apply them in practice. So if you're interested in that, there is a URL here. So I would encourage you to take a look at that and play with the code and try that on your own data. So just to sum up, first of all, it's very important when you have spatial data to understand what's the sampling design that you have, because it affects everything. And this is the difference between many traditional approaches and spatial data, that with spatial data, we need to consider also spatial relationships between our locations. And this makes a huge difference. Then another point, equally important, is about the proper evaluation. So we should think about our model evaluation in terms of the prediction. So do we want to predict in the places that are similar to our place or very different? Do we want to predict to places that are close or very far away? And then there are different tools to help us with that. So for example, there is this group of approaches called prediction domain adaptive cross-validation methods, which help you to realistically assess your models. And then there is also area of applicability. So the approach that we can say this place is similar to what our model's seen, and this one is very different. So probably we should not believe our model in those locations. Because we can predict everything everywhere, but we need to think if that makes any sense. And finally, there are tools that can help us with that. And of course, there are still many tools are in development, they are expanded, there are added, new features are often added. But I think this main core of the ideas is already there, and that could help you to put this in practice. So you can find those slides on my website at /ROM 2025. And I would just like to acknowledge that this kind of work would not be possible without the R packages that allow for that were made by many R developers. I also want to thank many GeoCompX contributors that make me smile often and look at great work that they do. And I also want to thank the members of the research group I am part of here that also push this envelope forward, and they work on those topics and help me understand them better. So thank you a lot for being with me, and I look forward to your questions.
Thank you, Jakub. So we have some questions here in the chat. Here we are. So from Marcia, how did you choose the model and nugget in VGM? Are those generally good values?
Yeah, so for this example, I just use a very simplified approach. So in this case, I just took my semi-variogram and just applied the fit.variogram. So this is an automatic fitting to the model based on some initial parameters. So in this case, the initial parameters are the type of the model, meaning what's the shape of this model, and a value of the nugget. But the actual function fit.variogram will adjust those values and will adjust this model. Often, this approach, in my experience, this approach is perfectly fine. So often this automatic fitting gives you good enough results, and but you can always do that by hand. You can also define different parameters manually. However, it depends on the problem. If the problem is simple enough, then this approach is perfectly fine. In some cases with more complex spatial relationships, then you are required to do that manually. Or often the manual approach is always better if you actually know what are the processes that are controlling the features that you are modeling. Because for some features, some approaches are better and some are worse. And then you can think about it in those terms of those different approaches. So of course, there's no like one easy answer here, but my experience is that I would usually start actually with, first of all, thinking about the problem. If I can actually actually argue for some kind of a model, and then just try that with the automatic approach. And then I often look if this automatic approach is actually giving me something similar to what I would do. If yes, that's perfect. If not, then I adjust that manually. And this manual adjustment usually happens about the nugget. So nugget is basically it's a measure of the uncertainty of the model regarding to its values and the local relationships. So usually this fit.variogram is not the best with modeling that. So I often put this value manually, but not always. It depends on the case.
Okay. The next question is AOA, so the area of application, analogous to MES, multivariate environmental similarity surface, and MOP, mobility oriented parity?
I've never heard of MOP. I think I read something about the MES approach. And I don't remember the details, so I cannot answer fully if that's similar, but I would guess it is, because they are so this approach here for this talk is called area of applicability, and it's focused broadly on the spatial machine learning, but the same idea is not only valid here. So it's valid to many different problems, not only even spatial problems. So I think that the MES approach and similar are often also used in ecology, etc. But there are also often approaches about like medical sciences. Like, okay, we create a model and we want to predict that model, but now we have some cases that the model never seen those values of, and we also should not use that. There is also a package in R called, I think, applicable or similar that also do that. So they are, I think, the similar ideas, the similar ways of thinking are coming from different angles, because this is I think, very general problem that we want to predict things, but we predict things based on the relationships between values, but our model have not seen many of those relationships. And then what should we do? And in the past, people mostly ignore that and say like, oh, let's just have a map. But in the last few years, I think this is more and more concerned that people can see that. And people say, oh, okay, maybe we were too optimistic with our model evaluation, or maybe we actually don't have an idea what happens in this remote place.
Okay, I have a question from Maria. How could I incorporate time variables in this type of model? I would like to make predictions of deforestation and LUC.
Yeah, it's a very good question. So I have a two-part answer, and the first part is I don't exactly know how to, but I'm very interested to work on that. But the second part of this answer is here today I show this general idea of this prediction domain adaptive cross-validation. So then the idea is that our cross-validation adapts to our prediction scenario. So I think with the spatial temporal problems, we just need to try to think about how we can take this approach and extend that to time. And with time, the difference between space and time, there are of course many, but one important difference is that with time we have a direction. So with space, we can divide space into folds, and I can say, oh, I have a fold here and here. So build a model on this fold here and here and predict on this. But I don't care about the order. But with time, there is a directionality of time. So probably my naive approach would be to divide the data based on the temporal structure, meaning that the data that is built on the model from the data for example, earlier data from the deforestation from some years previously, and then evaluate that on the independent sample of the next few years. And this way, you don't have this leakage between the different years that, oh, we evaluated our model based on the data from year X, but we also have trained that on the data the year before and after. That's probably too optimistic. So probably we should have it that way. That being said, I am fairly certain that in the cast package in R, Hannah Meyer, she added some kind of a spatial temporal validation method as well. So if you are interested in that kind of approaches, I would also encourage you to take a look at that. So I think this is what was I think developed 6-7 years ago. I think there is still space and to improve that and think about it better. But that would be my first step, to go there, take a look at that, and then try to maybe also look from the filter of the things I showed today.
Okay, thank you. And now a question from Nicolo. In the context of predictive modeling for spatial physical phenomena, do you believe that unseen data primarily consist of instances where insufficient covariates are available to adequately characterize the domain? Tell me if you want me to read that again.
Yeah, you can read it once more, and it will also give me some more time to think about it.
Yeah. In the context of predictive modeling for spatial physical phenomena, do you believe that unseen data, primarily consisting of instances where insufficient covariates are available to adequately characterize the domain?
So I think I mostly work with environmental data, and then with those environmental data, especially in a current age, it's even more important to have field work and have a sample from actual measurements. And some measurements are easy to get, but most of them are hard to get and expensive or impossible. Like it's maybe expensive to have like a dense network of sensors in the Netherlands, but it's impossible to have a dense sensors in the middle of Amazon, for example, or on some more remote mountain areas. So then the question is, what can we do and how we can improve? And for some areas, for sure, we can make improvements. There are often examples about the biases in different variables related to ecological studies, where most of the samples are from Europe and North America, but we have very minimal information from, let's say, Africa. And this could be improved. We know about this problem, so we probably should put more resources to do that. And then it's possible to improve and expand on that. This is the side of the outcome variable, but there is also a side of the predictors variable, because in this case I've shown you that I use 4 predictors, including elevation and some climatic variables. But then the question is also, can we actually find all of the predictors that make sense? Can we actually measure everything that relates to the things that we are interested in? Like often we use satellite data, but from the satellite we just look from the top and we try to measure something from the top. But can we actually see the same things that the plants need, or the animals are actually, and their relationships between them, or interactions, or their movement relates to? And I think this is an extremely complicated thing to do, because with those kind of approaches, we mostly work with proxies. And sometimes we work with proxy of a proxy of a proxy. And this makes this whole situation harder. But then I think that's why the angle I showed you today. So today, what I wanted to show was more about being honest to yourself. So more about how we can be more trustworthy, how we can be more reliable, how much we can actually believe the models we develop. And then if we actually know that, if we know, okay, my model works here, but has no idea about relationship there, this is new knowledge. This is, okay, so maybe we can work on that. And the same with those quality measures. If in the previous, I thought, okay, my RMSE of my model is 1, but then I actually made the proper validation and it's 5, so my model is not practical anymore. And then maybe this is not the model I should use, so maybe those are not the predictors I should be using. And I think this is, in a strange way, final model validation could be the first step, not the last step. It could be just the step that we are actually understanding our limitations, and but in this positive way, we can be pushed to improve on them. And I've seen a blog post a few days ago about, maybe I'm paraphrasing, but the blog post would that in the last decades, R-squared values in ecology are getting lower and lower. And I think this will be, or is the same for machine learning currently, that we will see papers getting larger and larger R-squared and lower and lower, larger RMSE and lower R-squared in the next few years, because we are getting better at actually properly validating our models. We are getting better at actually understanding them. And hopefully then we could also be better at getting proper and better predictions.
Yes, I think absolutely.
And sorry to provide that very long answer, but then is also one aspect that there are many aspects I have not touched today, but one aspect that also relates to that is explainability. That we should also, it's not only about getting a number, it's not also about getting a map. It's also about being able to understand what happens there. And then there are also many tools and many approaches or how we can explain and look at the map and open this black box, if we are using the black box method, and try to understand. And then that's why I think this domain knowledge, or at least domain intuition, is needed, because with this intuition, with this knowledge, we can actually put some of the models in question, or maybe be more confident with some of the models.
Okay, thank you. The next question is from Toyin. Could kernel density estimation be used to create a continuous map for this use case? This
So-
was at 7 o'clock, so I think it was referring to oh, I can't see your slides anymore, sorry, but does that make sense?
Yeah, so the method that was mentioned, KDE, is a method that takes points and then tries to create a continuous map from those points. But usually those methods, like this kind of density estimation, at least in this basic form, is about the points density. So it will give us a map where we have more points and less points. And in this case, it's different because for each point we have a value. So we don't want to actually just have a density map where we have more points or less, because our points are not an information. The actual information is the value in the points. So in this approach, for this problem, this approach is not useful. This kind of approach would be useful if you, for example, have points of some kind of a crime, and then we want to find locations where this crime happens more often or less often, for example, and then we can get this map of density of different types of crimes.
Okay. Our next question is from Federica. Federica, do you want to ask your question?
Yeah. So I practice it a bit with this data, such as the bioclim data. And so sometimes I found very difficult to be able to load all data and things. So in terms of space and time, loading time, can you like have just like simple rule of thumb to know how to deal with this large data? Because you said that you use like satellite images and things. So if you on top of that add the bioclim extra covariates and things, so it's gonna be like a bit of a work. So how do you deal with that? What type of computer capacity is needed, and so how do you do that basically?
So I think there are two axes to this to answer to this question, because one axis is basically about what kind of data we have, and then what kind of method we will use for that data. So for this talk, I focus on this example with a few hundreds of points scattered over a large area. And then for this, as you've seen, just a simple laptop is enough to run all of this code in a few minutes. So then we don't need to worry about this approach too much. But on the other hand, if we look at the problems where we have hundreds of like thousands or tens of thousands or 100,000 points, then we are going probably more into deep learning approaches, and then of course we would need to have usually larger computers or supercomputers that will apply to that, and then we could also do that from R, but we will just write our code in R and we call that code from some remote location, and then we'll use that. So then it's this dimension. But then when it comes to satellite data and spatial data in general, and the size of this data, it also depends on do we actually need the data of this size? Because, for example, if I have 100 points over the whole South America, I probably should not predict in 10 meters resolution because then this 10-meter resolution, I'm not catching those relationships in this resolution. So again, I'm just fooling myself. So probably I should start by decreasing resolution of my data and then making the data smaller, then making the data more manageable, because other way around, I'm actually fooling myself. With geostatistics, it's also possible to use some parameters that allows to improve that. So there is a parameter called nmax, which tells you how many points you want to calculate this relationship with, and this also allows you to maybe deal that with a little bit with that. With spatial points, with spatial data, we also, I think in the last few years, there is a more growing move toward approaches related to cloud, using cloud data and cloud approaches. So there are new data formats that basically you just work with the parts of data, or you just call the parts of data from the either database or a file. So we have file formats like Arrow, GeoParquet, Cloud Optimized GeoTIFF, ZAR, etc. Then we, instead of reading all of the data, we just read the data that we need. Or with like databases, like now there's a spatial extension to DuckDB, there is a Sedona DB. So there are different database approaches that we don't think about actually putting all of our data in memory, but we just try to look at our data from the angle of only the part of the data we need. And then, of course, the question is, do we do that from our own computer, or do we use our computer in the sense as a terminal to call that from some other locations?
Yeah. Okay, but I have another quick question, just a bit of like an explanation, what the difference between using the predict function from Terra package other than just the base R predict function. What?
Yeah, so in general, the Terra predict is just a wrapper over the predict function, but it's very useful because it's aware of spatial rasters, at least of the Terra spatial raster, meaning that, for example, if we have a spatial data, one of the features in spatial data, spatial raster data, is that we have often NA data. So we have, like in the South America, we have cells of the ocean which are masked as NA. And then the Terra predict will know about it. So we can use just na.rm equals true, and it will not predict into the ocean, which we know that should not be done, but some models would do that. Some models would just predict into the whole area, but with this approach, we do not. And then the output, so with the Terra predict, we provide what's the raster we want to predict in, and then at the end, we are also getting a raster directly. So we do not need to be responsible for getting the predictions as points or as just a table and then putting that into a spatial format. It directly gives us back this raster in a spatial format.
Thank you.
Okay, I think we're at the end of the questions. If anyone has any more questions, they can pop them in the chat now. Last chance. No? Okay. So, oh, hang on. No, something just appeared. Right, from Peter. Hi, apologies for a bit of a local query. Would you recommend if any optimal sources of geocoordinates of buildings located in Poland? I am aware of Google Service or Geoportal and some others. The query is more on your experience of the most efficient way of gathering data for example, 1,000K locations, which either require accessing any provider from R, but the service may not manage such numerous sets of observations. It may be managed by download of available files, including all addresses in Poland. However, the files are of huge volume, 6 giga, and R may not upload them and manage them efficiently.
Yeah, so when it comes to those kind of data, so in Poland we have this product that is provided by the main geodesy organization, and gladly there is a package in R called rGugig that I think also includes that. So there are in Poland data gladly in the last few years ago that the law changed and tons of data became publicly available, including orthophoto maps and also this kind of data, including like roads and buildings, etc. And this R package called rGugig has connections to all of those subsets. So I think they are divided into the main regions in Poland, but then you can download that. If the data is still too large for you to operate, what you can do is that you can try to convert this data into some format. So you can use packages like Google Utils, which is basically you can use this package to convert the data, so this large data, into those newest file formats, like GeoPackage or GeoParquet, and then you can use some queries just to read the data you want. But if you have a more detailed question, you can just email me and I will take a look and send you some links.
Okay, thank you very much. Okay, so I think we are at the end of the presentation now and the questions. Yeah, okay. Thank you so much, Jakub. That has been such an interesting talk and very, very helpful. It's really, I think makes a lot of us feel a lot better about some of those validation numbers that come out sometimes, and looking at whether they are really as good as they say they are. And we will be putting the recording onto YouTube in a few days' time. So I think from everybody here, thank you very, very much.
Thank you, everyone. Thank you, Jakub.
Thank you, everyone.
Thanks a lot.
Thanks.